Very much, Hans. Hello everybody. It's my pleasure to have this talk for you about the arc furnace. As indicated by Hans already, one of the illustrations of what we call in general electromagnetic processing of materials. So I prepared a little program for this talk. I will, in the first point, give you an idea of the electrical arc furnace. Then, in the second paragraph, I will go into the context and technology-bound motives leading to an increasing relevance of the electric arc furnace. In the third point, some words, not too much, but some words about the impact of the electric arc furnace on the electrical system. And then last but not least, an outlook for further developments of the electric arc furnace. So first, the idea of the electric arc furnace. Let me start with making a general consideration. I think it's great that we can have this talk about the internet. So I see here on my list people from everywhere in Europe and even from India. So welcome everybody, and it's a great technology, this internet, that we can be connected in such an easy way. For me as a teacher, the internet gives me the idea that when teaching, we do no longer need to give information to people. So I'm well aware that if you spend 1 hour on the internet this afternoon instead of listening to this talk, you will be able to collect a lot of information of the electric arc furnace yourself. So I don't want to compete with the internet. What I want to do with you is to make a reasoning about possible applications of electric arc furnace. And therefore, I will not be too technical, of course not, but somewhere I will go a little into the technical issues in order that you should be able to appreciate by yourself this technology and, more importantly, to find by yourself possible new applications. So let's start with the idea of the electric arc furnace. In fact, it's a rather old idea. It started already by a patent taken by Werner Siemens in 1880. Here you see the scheme of what is the idea of an arc furnace. You see, I will here take my arrow. Here is an electrode, and the arc as such is between the bottom of the electrode and the top of the melting bath. So here in this very short distance, and I will later on in the presentation give you an order of magnitude of the distance. It's some 20 centimeters or so. So here in this short distance, you have an arc. That means ionization of air and the conduction of electrical current coming from the source here on the left of the picture over the connectors here and over the electrode, which is in graphite. Here, the conduction continues not by conducting material, but just by air, by ionized air. This we call an arc. So in fact, the arc furnace is a transfer of heat. It's a transfer of heat by radiation. The heat is radiated from the arc to the melting bath. The arc is at a very high temperature, 6,000 degrees Celsius, maybe sometimes 8,000, 9,000 degrees Celsius. So a huge amount of heat, and by radiation, the energy is by heat transfer radiated to the top of the melting bath. I will come back to more in detail to the components of the electric arc furnace. By the way, what you see here, the first idea published by Werner Siemens is a so-called direct current arc furnace. I will go on to this later on, but I can already tell you that in spite of the fact that it has already been patented by the end of the 19th century, its breakthrough of the DC, the direct current arc furnace, came quite late, in the 80s of the last century. Because of what reason? Well, because we need power electronics for the direct current production. I will come back to that later. So what is the primary material? What is the feed for an electric arc furnace? It is scrap. So the electric arc furnace is typical a recycling system. So you see here on this picture the idea of scrap, and this will be the feed for the electric arc furnace. I see that people have problems with the sound, so maybe I can try another phone to see if it can produce. So here we see on this slide number 5, what is the feed, what is the primary material offered to the system of the electric arc furnace. It is scrap. So that means the arc furnace is typically a recycling installation. And what is so exciting is that starting from this kind of stuff, so I take my arrow, so this kind here of rubbish, let's say, it is refrigerator doors, it is the metal coming from cars and so on, so material that can not be used any longer, and by means of the action of the arc furnace, we are able now, thanks to the progress of technology of the arc furnace, we are able now to make steel that is capable for production, for instance, for this cables. You see here a very nice picture of that famous bridge in the south of France, the Millau viaduct, very huge construction. And just to show you that out of scrap, so here, remember the previous slide, out of this, thanks to the arc furnace, we can make again high value material like construction steel, able to be fit into the most modern constructions. Now let's go to the arc furnace itself. Here is a principal scheme of what is an arc furnace. We start here at the top right corner, so the transformer. Then you have here the cables bringing the current to 3 electrodes. 3 electrodes means that we have an alternating current arc furnace. Not important for the moment. I will come back to that later when I make the difference with the direct current arc furnace. So here you have the arms bringing the current to the electrodes, which are constructed in graphite. These graphite electrodes sink into the bath that is here below. We have here already some figures. I will give more figures later on, but you can see that the capacity of this system is 120 tons of scrap that can be converted in high added value steel. The diameter of the vessel is 7.2 meters. Its height is 3.4 meters. The tap-to-tap time, so it's a batch process. That means you fill the basket, you sink the electrodes, you do the process, and after 30 minutes, you can start with another basket. So tap-to-tap time, 30 minutes. The electrical power amounts to 170 megavolt ampere. We have a capacity here, a production capacity of handling, that means melting, 240 tons per hour, and a yearly production of 1.8 million tons. Here, a real picture. So the same alternating current arc furnace. You see arms bringing the current to the graphite electrodes, 1, 2, and here behind the third graphite electrode. And another point is that here you have the extraction of dust. So therefore I put here the title environmental control, because in steel industry the dust production is very important. So what we have here for this electric arc furnace system, we have an aspiration of the dust coming out from the slag of the melt. I will show you pictures of the slag later on. So here, indeed, a picture of the slag. So this is, the slag is driving on the top of the melting bath. Here you see an operator who is pulling out the slag, because this slag can be used as a construction material. So this is solidified slag coming out as a byproduct of the electric arc furnace. And here you see a possible application of this slag, this solidified slag, in railway construction. So therefore, we put it here, turning dust into a commodity as a byproduct, a secondary product of the yield of an electric arc furnace. So now I will go a little bit more in detail between the alternating current electric arc furnace and then after that the direct current electric arc furnace. Why do we see immediately that this is the alternating current electric arc furnace? We see it because of the 3 electrodes. You see them here above the basket. The basket is below. Here this will go open. It will be filled with scrap. Then this will be lowered, touching the scrap, and then pulling upwards so that an arc can be produced between the bottom of the electrode and the top here inside of the melting bath. Let's go now to the electrical scheme of this alternating electric arc furnace. We have here on the left the transformer, the conductors bringing the current to the 1, 2, 3 graphite electrodes, and in the alternating current arc furnace we have 3 arcs, 1, 2, 3 arcs manifesting themselves between the bottom of the electrode and the top of the melting bath. The current is flowing from one phase to the other. We have here a bottom electrode, but that is just for earthing. So there is no huge current in this electrode. It's just for the earthing of the system. These are the 3 electrodes. After one tap, let's say, you see that they are gluing. They have this orange color because they are very hot, because of the very high current that they have conducted. What is very particular for the alternating current arc furnace is the wearing off of the 3 graphite electrodes. You see that it is oblique, it is slant. What is the reason? Well, the reason is explained here. The arc makes a movement, and it's easy to understand why. I have here a 2-phase system to simplify the explanation. Here one electrode, here a second electrode. It's clear that the arc of this first electrode is in the magnetic field created by the current in the second electrode. We have current and we have magnetic field. That means we have a Lorentz force that makes the arc move around. In which way? Well, this can be calculated analytically. I have here again the 3 electrodes, here in broken circles, 1 electrode, second electrode, 3 electrodes, third electrode for the 3-phase system. And here you see the circle of the movement of the arc. This is not without importance. That means if your system is unbalanced, you can have a stronger movement, for instance, of this face, and you have an enhanced erosion of the refractory of your vessel here, which is, of course, something you want to avoid. Let's go now to the other system, the direct current electric arc furnace. Why do we see that this is a direct current electric arc furnace? Because you only have one electrode arm here, one electrode. And the electrical scheme is a little bit different. Again, we have here a transformer. We have a rectifier because the grid offers alternating current. We want to rectify the alternating current. And then again, the lead bringing the current to the graphite electrode. Only one electrode plus a bottom electrode. So for the direct arc furnace, you have the full current going to the melt bath. So in principle quite the same, but the difference is in the direct current, of course. Then let's go to the wearing off of the graphite electrode in a direct current arc furnace. You see that the wearing off is even. It is not slant, it is not oblique like it was the case with the alternating current arc furnace. This is because you have always a movement here, but it is not a well-determined movement of the arc as it was the case in the alternating arc furnace. Here the movement of the arc is not driven by a Lorentz force. I have no magnetic field here created by another electrode because I have just one electrode. And the movement of the direct current arc is completely defined by thermal movement. So it's a thermal stochastic at random movement, and therefore you have this even wearing off of the only one graphite electrode for the direct current arc furnace. So this brings me to the next paragraph, where I want to summarize in a way the context and technology-bound motives leading to an increasing relevance of the electric arc furnace. So first of all, the technology-bound motives for the increasing relevance of the electric arc furnace. Let me start by saying you this. In the beginning, that means in the 70s of the last century, electric arc furnace was only capable of producing very basic steel products. So that means not the high-value construction steel, as we saw in that nice bridge some slides before, but commodity steel, let's say, steel that is used for barbered wire, for instance. And then thanks to technological developments, which are here inventorized, you see here, I will not go into the detail, but sidewall and roof water-cooled panels, oxygen gas burners, progress in metallurgy, the foaming slag, I will show some examples later on, the post-combustion, the intensive use of oxygen and carbon, all these technological developments had a huge impact on the performance of the electric arc furnace. Let's start here with considering the tap-to-tap time. So it was in the 70s of the last century about 180 minutes, so that means it took 3 hours before you could handle another basket of scrap. Now it has come only 30 minutes. Same for the electrical energy consumption. So from 650 kilowatt hours per ton, we are now at less than 300. And also the electrode consumption, remember these graphite system, and we have to take into account that the consumption of these graphite electrodes is a production cost as huge as the electricity cost in the exploitation of the arc furnace. So it's very important, and we see also for the electrode consumption, it is mentioned here on the right side, that you have a very beneficial reduction of electrode consumption. So these are some technology motives that can be an explanation why we have indeed an increasing relevance, an increasing breadth too, of the electric arc furnace system. Let me take just a moment to compare it with another system that is used in metallurgy, for instance, the induction furnace. The advantage of the electric arc furnace is that it has a higher capacity. Remember this very first slide where we spoke about 120 tons per basket. Then we also have a greater refining ability with the arc furnace because of the high temperature of the arc. So we are more able than is the case with induction furnace to melt lower grade scrap. That means scrap that is mixed with other products, maybe products that contain a lot of carbon. Thanks to the high temperature in the melting bath compared to induction furnace, with the electric arc furnace we are able to handle this lower grade scrap as well. What is a minor point compared to induction furnace, it is that the electric arc furnace has a higher impact on the electricity system. This can become clear when I will show you some figures later on. So this was about technology. Now let's see what are context-bound motives. That means motives in the economy, in the environment, the broader environment of industrial production that can be an explanation for the increasing relevance of the electric arc furnace. Well, the electric arc furnace has the advantage that it are more or less small unities compared to other unities in steel industry. It are, let's say, small unities. That means you can install them close to market. So you have the advantage of proximity to the market. Also, it's a recycling installation. So recycling, of course, is completely coherent with the present day's concern about a circular economy. You produce, and what you produce when it becomes obsolete, you will recycle it, you will put value again in it so that it can be recycled, and as we saw before, it can be recycled in a high value way. Another context-bound motive for the increasing relevance of the electric arc furnace is that in the electric arc furnace, scrap is used rather than iron core. So that means when it comes to CO2 emissions, these CO2 emissions are completely linked to the CO2 emissions produced by electricity generation. You use electricity as the input in your production process, so you have to consider the CO2 emissions of your electricity generation system. The environmental control is quite well done, let's say. Think about that dust aspiration system. And then I think this is very important, really very important. We are now entering the age, well, I hope we can enter the age, we can fully enter the age of renewable energies. And when you say renewable energies, of course, electricity systems are the only way of using the energy. Electricity as making the link between your renewable source, the sun or the wind, and your application. Yes, then a few words, only a few words to assess the impact of the electric arc furnace on the electrical system. Here I put for, let's say, a general system. It's not that important, but which kind of system for electrical arc. But here, a 50 megawatt alternating current electric arc furnace. Just to give you some order of magnitudes of figures that declare the impact on the electricity system. First of all, the phase voltage of this 50 megawatt electric arc furnace, 350 volt. So make no mistake, the electric arc furnace is connected to the high voltage grid. not because we need high voltage. On the contrary, we need high current because we need an arc. We need 60,000 ampere as current. We don't need high voltage, but we connect the electric arc furnace on the high voltage part of the grid because of the short circuit power, because you need a high power in your system. And you see here, you need 50 megawatt. The arc power is 50 megawatt. The losses are about 10%, so 5 megawatt is lost, which gives an all-round electrical efficiency of the electric arc furnace around 90%. And now I told already the arc is quite short. It's only 25 centimeters, let's say. So here for this system, you have 3 arcs of 25 centimeters, and these 3 arcs are able to give to the melting bath a power of 50 megawatt. So you see that it is really a huge electrical installation. Then another issue is the noise. So maybe you ask, what is the link between the noise and the electrical system? Well, I hope to make clear that for you. So here you see a registration in decibel of the noise level. On the axis perpendicular to the screen, you have the time. Zeit in Minuten, it comes from a German publication. So here, this axis, perpendicular on the screen, is the axis of time. What do we see? Well, in the beginning, at the starting time, we have an at random distribution of the noise level. Whereas after the tap time, around 30 minutes, we see peaks at 50 hertz, 100 hertz, 150. We see peaks of noise at the harmonics of the fundamental frequency. So that means in the beginning, the process and also the electrical signal is very chaotic. And only in the end, you have a nice resistive system. This can I make clear here in these graphs. It is a registration of the voltage and the voltage over the arc and the current through the arc during the process. Here is the beginning of the process. You see that the voltage of the system is very at random. Remember the noise, which was at the beginning also very at random. And here it becomes better when the process progresses. And at the end of the process, you have a purely resistive kind of heating. That means a very smooth manifestation of current and voltage. I go back to this noise spectrum because the noise level is very high with an arc furnace system. You see here up to 120 decibel. So it is a system that makes really a lot of noise, which is a drawback, of course, of this industrial installation. Then another more tricky, more nasty impact on the electrical system is the flicker problem. It is illustrated here. You have the line current in function of time. You see a 50 or 60 hertz signal, but you also see that the envelope here, this amplitude, is changing in magnitude at a low frequency. You can see this. When the frequency of this variation is less than 30 hertz, you see it with your eye, and it's really unsupportable. We call this flicker. It's a very huge problem. If you have an arc furnace near to a residential area, you have to take measure to solve this problem of flicker. Well, here again, because I want to explain in 2 words why you have this problem, especially with the alternating current arc furnace and less with the direct current furnace. So here again, the picture that we already showed for the alternating current arc furnace. And here is what is called the circular diagram. I will not go into the details, but on the horizontal axis, you have reactive power of the system. On the vertical axis, you have active power, so the heat in the arc, let's say. Where is the working point of our system? Let's say it's not completely true, but it's a good approximation here on top of this circle. And what do we see? If you have a slight variation in active power, which you will always have in a melting process, you have an enlarged variation in reactive power. And that's the reason why you get flicker, because reactive power is responsible for the voltage of your electrical grid. So a slight variation, unavoidable in the melting process of active power, leading to a huge variation in reactive power, give this huge variation at a low frequency in your electrical system that we call flicker. Now I want to make clear, also in a few words, I can make clear for you, I think, why you have not that much this flicker problem with the direct current electrical furnace. First of all, let me go back maybe to this system, the alternating current electric arc furnace. And, well, how do we regulate power here? We are here in a high power application, so we want to control power. How do we control? Just by pulling up the electrodes, making the arc longer or shorter. That makes us go around here on the circle of diagram in active power. So the power regulation with the alternating current arc furnace is doing by lifting or sinking the 3 electrodes. Now we go to the direct current arc furnace. How do we regulate power here? We can do it in the same way, lifting or sinking the graphite electrode, but because we have a rectifier, we can also have a secondary, more fine regulation of power by the working of the rectifier. We can, by means of power electronics, we can influence the current through the melting bath. So the power regulation in a direct current arc furnace is much more fine than in an alternating current arc furnace. So here you have the circle diagram for the direct current arc furnace. Again, on horizontal axis, reactive power, on vertical axis, active power. Where is the working point here? Well, for reasons of smooth production, we keep it at 45 degrees. But that means that the unavoidable variation in active power gives not a magnification of variation in reactive power. So with direct current arc furnace, we have less or not that so a nasty flicker problem. To summarize, in a very short way, the power quality issues illustrating the impact on the electricity system for alternating current arc furnace and to compare it with direct current arc furnace. We have a huge flicker problem with alternating current arc furnace. We have maybe more a problem of harmonics with the direct current arc furnace because of the working of the rectifier. And also because we have just one electrode, maybe more unbalances with the direct current arc furnace. And then I come to my last paragraph. Let's have an outlook now for further developments of the electric arc furnace. Here I made a short analysis coming from the Steel Statistical Yearbook 2016, published by the World Steel Association. You see here over the years, here these bars on the top are representing the total worldwide production of steel. And here in the dark colored bars, you see the production of steel by means of electric arc furnace. Therefore, I think here we cannot conclude that the electric arc furnace is increasing, the application of the electric arc furnace is increasing in steel industry. It is debated. It is a controversial subject. Some authors, they state that the electric arc furnace applications are increasing in steel industry. Others say no, they are more or less stable. I think that, well, we can maybe discuss it later, but let's skip this for now and see that to other industrial sectors where electric arc furnace can be applied. of course, in the production of iron and steel, the examples we saw up to now, in smitheries and foundry industry, also in non-ferrous metals, but also in cement, lime, and magnesium oxide manufacturing industry. Also, application of electric arc furnace in the glass manufacturing industry, and also in large volume organic chemical industry. I have here a picture for you of the electric arc furnace, alternating current, because I have 1, 2, 3 graphite electrodes, and here this the top of the melting bath. It is not metallic material; it is a mineral material, to show you that you can take advantage of the huge value of the temperature of the system to put added value in a lot of materials and also in minerals and ceramics. So further developments, technical developments that were already responsible for the breakthrough of the electric arc furnace technology and that are promising for widening the application field of this EPM system are the injection of oxygen to produce what is called chemical heat, and also the injection of carbon, granular coal, to reduce the iron oxides and to become a better quality of your melting bath. So you see here the injection of these chemical substances by so-called lenses through the vessel, through the wall of the vessel above the melting bath. These kind of injections of oxygen and of carbon, they give a very beneficial effect, the so-called foamy slag. You see here in red on the bottom, let's say the melting bath, so the metal, let's say. On top of the metal you have the dust material, the carbon material, so that we call the slag. And then thanks to the lensing of oxygen and of carbon, you arrive at an arc that is completely submerged in the slag, which gives a very good performance of the production. We call this foamy slag. So you have a reduction of the heat losses through radiation from the melt. So the slag forms a covering of the melt, which means that you have an increase of electric power efficiency by at least 20%. And because we are here feeding the system with a very expensive source of energy, electricity, so that is a big deal, let's say. And also the foamy slag technology gives a beneficial reduction of the tap-to-tap time of the system. Okay, so as I told you, on internet you can find a lot of information about electric arc furnace. It is always under study. People all over the world try to improve the performance. I put here just some references. These are the references that I used to make this presentation for you. So if you consult it on internet, you will find some more explanation on the pictures that I show to you. So here I come to an end of my presentation, not to the end of my availability, because maybe you want to discuss or you want to put forward some questions, and I will be happy to go into that. Thank you very much for your attention.